Hi, I'm Toru Tanzawa. Thanks for coming. I'm going to have a series tutorial presentation on charge pump circuits. Please send me email to this address if you have any question. If you have any more interest on this topic, please visit this website. You may find another interesting things. Uh, This slide shows the agenda for this series tutorial. I'm start with the DC-DC charge pump, then the AC-DC charge pump. In the first portion, I'm start with steady-state circuit equation in low-frequency operation. Then I'm going to expand that model to dynamic behavior and its equivalent circuit model. The steady-state circuit equation is expanded into wider frequency range, which should have the low-frequency operation model at the extreme condition. And another aspect of the charge pump is power efficiency. And also I'm going to address optimum designs. So optimization is various kinds, such as minimizing the circuit area and maximizing the power efficiency and so on. After that, I'm going to focus on the AC/DC charge pump, which just for the steady-state circuit equation in wide frequency range. Dixon shows this topology for a charge pump circuit, which is suitable for the integration. The charge pump has many series diodes and many capacitors connected in parallel like this. The capacitors are driven by clock phi and phi 2, which have the two-phase like this. So design parameters are these. VDD is input to the input terminal as well as input to the oscillator. And therefore clock amplitude of phi 1 and phi 2 is also VDD. The threshold voltage of the diodes is expressed by VT. N indicates the number of stages. So as you see, the one capacitor and one diode composes one unit. You can put many units like this. So in this case, n equal 2. C indicates the capacitance of each capacitor. Output voltage VP and output current IPP. Of course, IPP has time-varying components, and so in this IPP shows the average output current over a period. And also the F shows the clock frequency. Then I'm going to show the how to get the steady state circuit equation in low frequency operation. If you look at the first and second stages from generally n stages charge bounds, this portion is capacitor and diode composes the first stage, and here's the second stage. Here's the second stage. And here's the third stage, and so on. And height indicates the voltage at each node. So in this situation, figure A, the clock to the first capacitor is now grounded. Therefore, second stage clock is now VDD. Therefore, the capacitor bottom plate is grounded, and the second capacitor bottom plate is now VDD. As you see, this first the diodes turned on, and until this diode flows the current until this node goes up to VDD minus VT. So slow switching limit, or very low frequency condition, indicates that the diode turns off by the half clock. And therefore, after half clock, then this voltage goes up to VDD minus VT. This portion indicates top plate plastic capacitance, CT. And this large Q and small q indicates first stage capacitance, how much charge is stored in the main capacitor, and top plate plastic capacitance CT. So because V1 is given by this, and therefore Q1, those Q1s are respectively given by this equation. Then the next half clock, the bottom plate of the first capacitor goes up to VDD. Then after half cycle time passes, and at the moment those capacitors stores the amount of charges like this, Q1 minus and Q1 minus. And this small q is now defined as how much charges transferred during half period from first stage to second stage. And therefore, this amount of charge, transfer charge, is given by initial amount of charge minus the final amount of charge, like this. This Q1 minus is given by this because the top plate voltage is V1 minus and the bottom plate is now VDD. Small q1 minus is now expressed by this equation. And when you use these equations, then you get this equation. You can show V1 minus with given parameters like this. This kind of method can be done for the other stages. In this example, if you focus on this, the second stage capacitance, you get the similar equation like this. In this second stage, these amount of charges are initial ones, and these charges are the final ones. Therefore, the difference between the two is exactly the same as the transfer charge to the next stage. Also, you can show the V2 with Q2 and bottom plate voltage VDD. Through these equations you get here, and the previous slide shows V1 minus, and now we have V2 minus. Then this equation holds during this period as well as this period. Therefore, these two V1 minus and V2 minus related with this equation. This can valid. This is valid as far as the clock frequency is sufficiently low. Then those equations results in this equation. The amount of charge Q2 in this period, you can show with these parameters, including small q. You can extend that Q1 and Q2 expressions to the following stages. For example, Q3 is expressed by this. Then you can guess the other odd number stages charge Q to k minus 1. So let's look at this equation is valid when k equal 2, which is 3. If you input k of 2, then you get this value, and also this value 3, and also 2q here. And you also have the charge Q at even number stages, like this. You can check if this is correct with by inputting a K of 1. Then now you can have all the Q's are expressed by BDD, C, alpha, and BT, and small q. And the last equation is from the final stage, which is connected to output voltage V out. This equation holds if you look at this. And when supposing your charge pump has even number of stages, then the last capacitance is even number. And then you should input this expression into here. You get the final equation like this. And this small q is the charges transferred during one period to output. So if you normalize small q with one period, then that number is becoming the output average current. So this is the equation showing the relationship between output voltage and output current. So this is it. Then it can be expressed with the following three equations. And so output current is given by this form. If you look at here, and if you define these values as Vmax, and if you define this term with RPMP, so Vmax and the RPMP are expressed by these equations. And at this point, this output voltage and current is becoming a Thevenin's equivalent circuit model. You can treat the Dixon charge pump with a very simple circuit which only has two independent values, Vmax and RPMP. And this circuit model expresses these characteristics. And this is the steady state equation model. Thanks. If you feel the reduction to the final the voltage current result a little complicated, then there is another intuitive derivation of that model. You may have the assumption of the charge pump modeled by Thevenin's circuit, which should have voltage source and the output impedance. Let's look at the charge pump with the stage number of 1, and the circuit is simplified like this. Input voltage and output voltage is terminated to ground. Then the diode is modeled with the simple switch phi and phi bar. And during this period, the first capacitor is charged up to V. Then the amount of charge is given by Cp. After this operation, the switch is flipped, and then during this period, the amount of charge is discharged to the ground. If you think this is the average current during cycle time, then you should calculate I equal Q over T, and you know Q is Cv. And if you vary this equation into V equals something times I, this factor must have a unit of resistance, which we call it as RPMP. Then this value must be T over C based on this equation. So this value has an ohm as a unit, and because the charge pump with the number stage of 1 has this amount of equivalent resistance, then if you extend that idea into arbitrary number of stages like this, then it is fair to replace switch plus capacitor as a single resistor whose value is T over C. And the number of N is equivalent to the unit number of switch plus capacitor. Therefore, unit resistor, equivalent resistor is connected in series. As a result, it is easy to combine those series resistance into a single resistance. That resistance value is now N times T over C. So this is the basic fundamental equivalent resistance for the charge pump. Next, let's look at the maximum output voltage, V max. And again, let's start with the number stage of 1. So during the first half period, this node is charged up to VDD minus VT, where VT is the threshold voltage of this diode. Then the next half period, the bottom plate is raised up to VDD. Therefore, the top node is boosted up by VDD, resulting in this amount of voltage. And because of this another diode, and then the output is this value as max. If you imagine and that this procedure can be executed to arbitrary number of stage, then this factor 2 should become N plus 1 for N stage charge pump circuit, because it is easy to recognize that the maximum output voltage is this value, because each diode you have a voltage gain of this amount of voltage, then the number of diodes is n plus 1. In summary, we have Vmax and RPMP with these the design parameters like this. So at this point, we have this equivalent circuit, and this assumption was actually correct.